Hello everyone. Today I will presenting the paper Beyond WL, a quantitative framework for graph neural network expressiveness. This work is primarily focused on improving our understanding of the expressive power for graph neural networks. This paper is published in SALR on 2024. Let me start by giving you an outline of today's talk. We will begin by discussing the expressive power of graph neural networks by reviewing some previous work. And then we will go into a novel concept introduced in this paper, homomorphism expressivity. And then we will explore how this framework applies to various graph neural network architectures. And then we will end up with some experimental results. So let's begin with introduction. Graph neural networks have gained a lot of attractions as the leading approach for analyzing and processing data with graph structured representations. However, as graph neural networks evolve, it becomes increasingly important to quantify their expressive power in a precise way. This is where this paper makes its contribution. So imagine a graph neural network used in a social network. So the nodes are represented as users. The nodes represent users, and the edges represent their interactions. So if the graph neural network is expressive enough, it could detect complex structures like communities or cliques within the network. And this will allow this graph neural net model to predict the social trends or the most influential social users. So another use case is molecular chemistry, where the graph neural networks are used to predict the biological activities of molecular based on their structures. The more expressive the graph neural network, the better it can understand the relationships between the atoms and then it can predict the molecular behavior. So what is the expressive power of graph neural networks? This power is a crucial measurement of a neural network to distinguish between different graph structures. It will capture the node relationships and represent the underlying graph structure information. So a graph neural network able to learn a general function on graphs. This is the important questions we want to solve. They want to solve in this paper. So if a graph neural network is expressive enough, it should be able to learn any general functions that maps graph inputs to desired outputs based on the different research tasks. For example, node classification, graph classification. And if with a more advanced graph neural networks, it will have a higher expressiveness, and it can better approximate general functions on graphs by capturing more structured information. So why we need to do research on the expressive power of graph neural networks? Because this is important for distinguishing the graph structure, capturing the complex patterns in the graphs. And then this advantage can generalize into real-world applications like moleculars for drug discovery or patterns in social networks. Before we dive deeper, let's briefly revisit the previous work on the expressiveness of graph neural network. So one direction is based on the WL test. It is a graph isomorphism test that checks whether two graphs are equivariant by iteratively refining the labels of the nodes based on their neighbors. So for standard message passing graph neural networks, they have been proved as expressive as the 1WL test. This means such graph neural networks can struggle to distinguish certain graph structures that are non-isomorphisms, but indistinguishable to the 1WL test. There are many non-isomorphism graphs that cannot be distinguished by the 1WL test. For example, consider two graphs with same local structure around each node, but with different global properties, like cycles, clicks. The WL test would fail to distinguish them because the WL test only looks at the local neighborhoods. Therefore, to improve the expressiveness, some research focusing on proposed higher order graph neural networks to go beyond this limitation. But these networks based on the higher order WL task, and such framework will create a challenge, will create the computational issues. Therefore, in another line of the expressive power of graph neural network is substructure-based graph neural networks. So recent work has shown that the standard message passing neural networks cannot encode structure information, such as counting cycles or clicks in a graph. So many graph neural networks may also fail to encode this critical structure information. To improve this, many work focuses on pre-process these substructures and use them as input to design more expressive graph neural network. However, this model only show restricted aspects of expressivity. And this leads us to a natural question. How can we quantitatively measure the expressiveness power of the proposed graph neural network? Now let's turn our attention to the core concept of this paper, homomorphism expressivity. So given a graph neural network model, the family of the substructure M can be encoded. The family of the substructures M can encoded, denoted as F, can naturally be viewed as a measure of expressivity. So by identifying Fm for each model, the expressive power of different models can be quantitatively compared using some set inclusion relation and set difference. So this framework allows us to systematically compare the expressiveness among different graph neural networks. And this can be quantitative by examining which substructures they can count. So what exactly is homomorphism? Here is a formal definition. Given two graphs F and G, and a homomorphism is a mapping from F to G, such that it can preserve the local structures for vertex labels and edge relations. For example, it is noted that this mapping is injective, which means it maps different vertices in F to different vertices in G. And the figure the following figure is a valid structure preserving mapping from the left graph into the right one. So for example, for edge relation, V1 maps to the node W1 and V2 maps to the node W3. And there is a node there is an edge between V1 and V2, and we can see there is also an edge between W1 and W3. So this is a valid structure preserving mapping. This is a homomorphism. This is a homomorphism. And then, therefore, a graph neural network can encode the substructure F in terms of the homomorphism if for any input graph G, the computed graph representation of G can count the number of homomorphism from F to G. So we denote the number of homomorphism as the hom FG. Now, this is the formal definition of homomorphism expressivity of a graph neural network model. That is, given a GNN model M and a graph G, we use X to denote the graph representation of G computed by the model M. Therefore, the homomorphism expressivity of GNN is a family of labeled graphs satisfying the following conditions. That is, for any two graphs G and H, the representation of two graphs will be equal if and only if the hom FG and hom FH are equal for all the substructures in this set. So FM is maximal. FM is maximal when for any graph F in this set there exists a pair of graph G and H such that the representation are same, but the hom FG are not hom count are not same. So as a simple example, we consider a maximally expressive GNN that can solve the graph isomorphism problem. It computes the same representation for two graphs if and only if they are isomorphism. Then this FM contains all the graphs. So why we use the homomorphism counting instead of subgraph counting? There are two reasons. The first, homomorphism counting is more fundamental other than the subgraph counting. And second, it aligns more with graph neural networks. Because the aggregation mechanism used in the graph neural network layer only encoded the local structure. And the second information I want to talk is why we do not use the WL test. So the WL test can be too coarse for practical graph neural networks. So homomorphism expressivity provides a more quantitative measure of how much structure of a graph neural network can encode. This allows us to directly compare different graph neural networks. Then this paper provides a clear way to compare two models based on their expressive power. That is, for any two models M1 and M2, if the family of the substructures that M1 can encode is a subset of those that M2 can encode, then we say that M2 is strictly more expressive. So specifically, for any graph G and H, the equal representation of the model M2 implies the equal representation of the model 1. Okay, then this paper then presents the expressiveness results on several popular graph neural networks. So Message passing graph neural networks are a classic example in this framework. So this slide shows the simplest message passing mechanism. It maintains color, or we can say representation for each vertex in the graph. So at beginning, each node is assigned at beginning, each node will be assigned a label. And in each iteration, the representation of each node will be updated by aggregate the message from itself and its neighbors. And altogether, this information will go through a hash function. Then after we get a stable representation of each node, the graph representation can be defined by a multiset of the representation of each node in the graph. Okay, we can say that the computed node features, the computed node representation of an message passing graph neural network can be fully determined by the structure of the unfolding tree. So this figure shows an example of a graph where certain nodes are considered, some nodes are considered to be equivariant and others can be considered be non-equivariant. So the unfolding process is a way to represent how a graph neural network or some other graph algorithm will see the neighborhoods around each node by expanding the graph outwards to a certain depth. So for the non-equivariant node B, so you can see that the unfolding tree captures the different neighborhoods of the graphs, and it will maintain its structure. So for the equivariant node A, the unfolding tree shows that its neighborhood is indistinguishable from that of other equivariant nodes D. So leading to the same structure being repeated at some certain depths. So we can find that the representation of one of each node in the graph contains the home numbers of this node for all such rooted tree FW. Therefore, we can define the home number of over the whole graph as the summation among each node. So the graph representation X will encode the home FG for all such trees F. Therefore, the paper have its first results. The homomorphism expressivity of the message passing graph neural network. That is a set of F, a set of subgraph F, where each graph is a forest. So then we move to the next graph neural network. It is a subgraph graph neural network. This is an extension of the traditional message passing graph neural network that it will treat each node in a graph as a special vertex, and it will consider the subgraphs around that node. And here is how it works. So at beginning, the subgraph, it will assign each subgraph a label, and then for each iteration, it will also update the subgraph's representation by collecting the message from itself and its neighbors. And this iteration will stop when we got a stable color. So the node feature of the node feature of a graph U we is is defined as this equation and also the graph representation. They are all very similar to the message passing graph neural networks. Okay, so in general, if a substructure F can be counted by a graph neural network, F should admit a tree decomposition that aligns with the structure of the graph neural network unfolding tree. So this figure shows one example of the unfolding tree for the subgraph graph neural network framework. Okay, then before we introduce other graph neural networks, this paper also introduced a method to characterize the structure of the subgraphs. It is called nested ear decomposition. So that is, given a graph G, a net P is a partition of the edge set, into a sequence of some simple paths, and each path can be called ears. And these paths will satisfy the following conditions. There are three conditions, and in this decomposition process, we link the structure of the graph to how net represents graph decomposition using years. That is the sequence of edges forming the path, and it can also help us to identify the substructures within the graph. And this figure shows a nested ear decomposition process of this given graph. Okay, so given this given this nested ear decomposition, this paper further applying their framework to more graph neural network architectures, such as local graph networks and F graph neural networks. And this is the main results of this paper. And we can see that the expressive power is quantified by a set, and each element in this set indicate one variation of the net. Okay, then this figure represents a hierarchy of the GraphNet of the GN models in terms of their expressive power. So the higher order GN, like 2 GNs, 2 FWL GN, 3 GNs, are more powerful in terms of capturing complex graph structures. But as we mentioned before, they might also come with a higher computational costs. So for subgraph GNs and local GNs, they are also powerful, and they increase their expressiveness as the graph depths or local structures they can encode becomes more complex. And this hierarchy start from the simplest message passing neural network. Okay, this paper also extend the homomorphism concept to the node and edge level expressiveness. For example, the node level homomorphism expressivity of a GNN model, we use FNM to denote, and this is a family of connected rooted graphs. So it is very similar to the definition of the graph level expressiveness. So for any connected graph G and H, and for for any vertices U in G and V in G, the representation after the model of node U and V are equal if and only if their home count are equal for all the for all the for all the substructures in this set. And then for any connected rooted graph, there exists a pair of connected graph G and H, and also the vertices U and V, such that the representation are same, but the home number are not same. Okay, so now let's look at the experimental results. So, to test their theory, the authors conducted several experiments on synthetic tasks, including cycle counting and homomorphism counting. So the result shows that the model with higher homomorphism expressivity, like local 2GN and FGN, perform better at counting these substructures which are listed in the table. And also this is the experimental results on the cycle counting task. We can also see the local 2GN, high order GN perform better than other GN. So this confirms the theory that more expressive model translate into better performance on practical tasks. Okay, so in summary, this paper introduces a new quantitative framework for evaluating graph neural network expressiveness. And this framework offers a more complete understanding of how graph neural networks capture graph structures and provides a systematic way to compare different models. These findings also open up a new possibility for designing more expressive graph neural network architectures that can better handle the complex tasks in the practice. Okay, that is all of my presentation. So thank you for your attention.